into it. So first is Chris, who's recently joined CFM as of May. He's working on the iLaunch AM2 project with me and several of the rest of us. So Chris has finished his PhD project, which was a joint program between Swinburne and University of Stuttgart. And he is going to share some of what he did during his PhD today. So Chris, I'll stop sharing and over to you.
Thank you. Let me see if this is preparing my slides. Wonderful. Can you all see my slides?
Yep, perfect.
Slide. Okay, thank you. Yeah, thank you very much, Molly, for your introduction. Yeah, as you said, my name is Chris Mimra. Yeah, I've joined and just recently, and yeah, I've done what most moderators don't like at all. I've changed my topic last minute, but just slightly. I thought I'd make it a bit more broad, so it's more applicable to topics that we all cover in CFM. So my topic today is machine vision-based monitoring systems for composite manufacturing. And yeah, as Molly, I would also like to acknowledge the country. I'm actually based in Melbourne mainly. In 2 weeks I've been to Toowoomba as well, and I acknowledge a country here as well, which is country of the Kulin Nation. Pay respect to elders past and present. All right, let's dive into machine vision-based monitoring system in a production environment. So on the right-hand side, you see a picture that ChatGPT or our Microsoft Copilot generated when I asked it to create an image of a machine vision system that monitors carbon fiber composite manufacturing line. And yeah, it does have some similarity to our machines and production line in P11. I mean, you see all the robots, you see this automated line, you see barely any humans, and I don't mean that as an insult, no, the opposite. No humans means it's an automized system, an automized production line. And this is what the aerospace, but also other industries need, highly automated production lines. And as part of that, we need an inspection system and monitoring system that is reliable and precise. And for that reason, more and more sensors, cameras, are introduced into the production line to inspect the part, the material, and guarantee a high quality. However, now the question is, with more and more data available, how do we actually process it? Because it's now too much data and too complex data to to evaluate by humans. So we need some novel evaluation methods. And the thread in this presentation is going to be if machine learning is the solution, or what algorithms might be best suitable to evaluate this large amount of data to automate the composite production. I've split this presentation into 5 sections. First, I would like to introduce machine vision and some of the principles. I would like to talk about knowledge-driven machine learning, and then 2 examples: the machine vision system for automated tape laying, which was, by the way, the original title of this presentation, and then also the applications for filament winding and filament placement, which we have in P11 in our lab. And I'll end with a conclusion and outlook. So let's dive right into the introduction into machine vision principles. I suppose there are not a lot of computer scientists here in this group, So I would like to start with some definitions and a very, very broad overview of some terminologies. So let's start with artificial intelligence. It's a very broad field, and it has multiple hundreds of subfields, subcategories, and yeah, it's not easy to actually define a categorization, a structure, because there are so many different ways to categorize it. But let's start with a definition. So AI is a theory and development of computer systems able to perform tasks normally requiring human intelligence. That means everything that we as humans usually do, if we teach that to a computer, to an automated system, that's AI. So one example is visual perception. So we can see and we can interpret what we see as humans. If we teach that to a computer, we have machine vision. Or as other example, language processing. We can speak, we can understand language. If we teach that to a computer system, we have language processing. Two other subfields of artificial intelligence that I would like to explain, because it's going to be important further on in this presentation, is those expert systems. So an expert system is based on rules. So to create an expert system, you first create a knowledge data bank of rules, how to interpret the data, what structure the data has. And based on these rules, you create strict algorithms to then evaluate the data. So that is very domain specific. That is heuristic, algorithmic, and it's very understandable because we as experts with our domain knowledge, we create those rules. So it's traceable. On the other hand, we have machine learning, and machine learning revolves about the data. So you gather a lot of data and then use this data to train your the network. So the network, everything that is taught is simply based on the data to make predictions, and that is very important. You don't get certain results. You just get predictions, the most likely result with machine learning. And one subgroup of machine learning are neural networks. I've just highlighted that because it's the most commonly used, maybe the most hyped architecture in machine learning. And what I would like to focus on is if this is just a hype or if we should actually use it in our production environments. Just as examples, I mentioned ChatGPT or Copilot earlier. It's a neural network which does language processing. Now it also does machine vision, creates those images. So that's on this side of this diagram, whereas a simple QR code scanner, you have very strict rules how QR code must look like. So that's a good example for an expert system. Some benefits and challenges or downsides of those different fields. So if you use machine learning, as I mentioned, it is data-driven, so you probably get less human bias in your results. There's still human bias because it's the architecture, the way you structure the system itself, the algorithm, that is just as important as the data itself. So there's still a lot of bias in a machine learning result or algorithm. However, maybe a bit less than if you do an expert system where you come up with all the rules. However, as you can see down there in the red field, machine learning is prone to bias from the training data, which is a big field right now, a big topic with ChatGPT and all those generative algorithms. Machine learning can find more complex relationships, and it can be more computational efficient. However, it's not explainable, and that's again where the expert system comes in play, because it is based on rules that we have created. Because it's very similar to a manual process, it is easier to explain it and therefore certify it for certain critical applications, such as aerospace. And yeah, there are some more upsides and downsides, but I think I've mentioned the most important ones. So the question now is, can we merge those two fields somehow? Can we create knowledge-driven machine learning systems to get the best of both worlds? And for that, I've prepared 3 different methods, which I would like to introduce. The first one is task splitting. So instead of computing the entire task by one system, you can split it and do one part of the task with an expert system, and then other tasks are, with neural networks, with machine learning. For example, there's for self-driving cars, if you have an image of the street in front of you and you need to know what signs they are, you can feed the entire image into a neural network, which needs to be a huge network and probably takes quite a while to evaluate the data. Or you can use an expert system first, because those signs, they follow very strict rules. They're always maybe next to the street, mounted on a pole. They have specific shapes, specific colors. So you can extract just the snippets of the sign and then do the interpretation with a neural network. And that can be much faster, can increase the explainability, but the flexibility can be reduced. So that's one option. The other option is physics-informed neural networks, which is a huge research field right now. So this method is very suitable if you have a very well-defined physical law. For example, in fluid dynamics or MRI or CT image reconstruction. For those, you have very precise physical models. For example, partial differential equations. And these can be combined with a neural network, which then leads to higher accuracy. And most importantly, it's physically consistent. So by combining those two, the neural network and the physical law, you can make sure that the results actually follow the physics. And it also works with limited data. For example, in fluid dynamics, if you have just very limited specific spots where you can measure, with this method, you can extrapolate it to the entire flow and predict the entire flow well. Yeah, so that is another option to merge those two fields. And the third one is that I would like to explain today is augmented training data. So as you might know, for neural networks, you often need, or you always need, a lot of training data. Especially in manufacturing environments, it's not always easy to capture that much data. So you can augment it, you can add artificial data. So in this case, if you know how the image looks, for example, that this is a measurement that you can see here of carbon fiber tapes with very specific features, characteristics in it. For example, that line in the middle, which is a gap, those dots on the sides. Those characteristics can be merged into a geometrical model, which then generates artificial data. And what I've been able to show in my PhD is that this can lead to higher accuracy, that it works with limited real data, and that you can balance your data set. For example, if this gap, this defect only occurs every 1,000 measurements, and you capture, let's say, 10,000 measurements, you only have 10 instances of this gap. So it's hard for the neural network to learn it. However, with this artificial data, you can balance the data set and create more occurrences of these specific characteristics, leading to, and therefore your knowledge, your specification of what you know about the data can flow into the neural network as well. And yeah, I'll go a bit more detailed into this approach with this example. So the machine vision system for automated tape laying, that was my focus during my PhD. So on the left bottom side, you can see that tape layer, and I've introduced a laser line sensor, which measures the layer. What you get from that sensor is this profile with the, as you can see in figure 8, top on the right-hand side, you can see those little slit gaps, welding spots, different features of the image already in this two-dimensional representation. And then by adding up all those different profiles, you can create a three-dimensional representation of the surface as illustrated in figure 10. So that works in line with the process in real time. Now, the only problem is we need to evaluate this data as quickly as it is captured. So for that, I've tried those two and compared those two fields, or approaches. On the top, you can see a rule-based algorithm. So I've created an expert system, which is based on different rules. For example, that defects, those gaps are always elongated. They have very distinct edges. They're always in one specific orientation. They're separated. All this is knowledge that I gathered from investigating the process. And with all those rules, I've created an expert system which evaluates the data quite reliably, actually. And then I compared it to a data-driven evaluation, which takes the image and creates this colored output file, where you can, in red you see overlaps, in blue you can see gaps, also fuzz balls. Those different features are then evaluated and detected by the neural network. And into that algorithm, I would like to dive in a bit deeper. Unfortunately, I don't see any time here on my screen, but I just hope I have a couple minutes left. So a convolutional neural network is what I've used. I don't want to go into too much details. However, what I want to say is on the left-hand side, you can see the input image. the scan from this laser scanner that I've introduced. And then it runs through different layers of this neural network. And the output is, as you saw, this this colored image where all the defects, all the characteristics are colored in, detected. And from this output image, you can easily do a measurement, for example, compare it to specifications, and then decide if the product is acceptable or if it needs to be scrapped. Let's quickly talk about the training process. As mentioned before, for neural networks, for machine learning, you need a very large training data set, and you need to train the data. And that's where I used this this augmented data approach that I've introduced earlier. So in the first phase of this training process, I trained the neural network with artificial data. I've had those 4-channel annotations. So annotations is the ground truth, the colored image that I've colored manually or semi-automatically, that distinguishes those 4 different characteristics. So that is the artificial data in the pre-training. Then in a second step, I trained with real data. And you can see here I've used 1,200 real images, real scanned images. Compared to other machine learning algorithms, this is not a lot. So some other machine learning approaches, they use millions and millions of data instances. However, as I mentioned, in production, it's very expensive, very time consuming to produce all this training data and also annotate it. So I can actually use it. So 1,200 for production environment, that is actually a very, very large data set. And that's what I've used to fine-tune the algorithm, which took another 13.5 hours to fine-tune it, to train it even further. But then in the application, the system is very quick, and actually with about 1/7 of a second, it's much quicker than the rule-based expert system, and produces those results in line with the system in real time. And the results, let's look at some of the training data and the results. So here you can see the 3 different pieces of input data. So on the left-hand side, the artificial data that was used in the pre-training, then real data used in the fine-tuning aspect, and then after applying it, the algorithm and actually using it in line, I fed in, for example, this input, and the output is shown here. So the annotation, the ground truth, is the left image, and the prediction by the neural network is on the right-hand side. And you can see even those tiny little fibers on that fringe, on the edge of this gap, even those are predicted in with this neural network. So it's very, very precise, very accurate. Another example is here. So you can see there's a tiny little gap, 2 edges on more the left half of the image. In the annotations, because it was so small, and in some areas the 2 tapes actually almost touch each other. In the annotations, I just defined it as pristine, as okay. But the algorithm, the machine learning network, was good enough to even pick up these tiny gaps. So that actually surprised myself how accurate it is, even in cases where the annotations were less precise. So that in this case, this machine learning network with this approach of augmented data for the training phase has worked very, very well. And now that after I've joined the CFM, I would like to extend this research onto filament winding and the filament placement process. And this is going to be a bit of an outlook, what my work is going to look like in our lab. So most of you might have seen or heard about the filament winding machine. Top right-hand side, you can see an example product. This process is used to produce tanks, for example, hydrogen tanks. It's very established in the industry. However, especially in these end contours, in those double curved areas, the fibers sometimes just slip off, which leads to a knockdown in mechanical properties. So currently we just measure the tension on the robot, on the applicator, and we look at it manually, but slight movements cannot be detected nowadays. So what I would like to do is introduce a camera that looks at those interesting areas and then detect even the slight movements of those fibers. So yeah, even if it's just a couple millimeters or a couple degrees, as you can see in that bottom image, that system should be able to detect it. But that's going to be a pure expert system, because I know all the rules how to evaluate the data. But then in the outlook, in future, we could map that and predict the effect on mechanical properties. And that's an application where machine learning can be very, very useful. So in this approach, we have this task splitting. So the evaluation of the image can be an expert system, whereas the interpretation can then be done by a machine learning network. And yeah, that brings me to my conclusion. So yeah, we've talked about the differences between machine learning and knowledge-driven expert systems, and both definitely have their space. And we should definitely try to find the best tool for the application on hand. So machine learning approaches can help if expert knowledge is unavailable or too complex to integrate into the system. However, if it's available, if we know enough about the data, the expert system is still a viable and very useful tool. So we always need to to weight up the challenges and benefits of machine learning towards the expert, compared to the expert system. However, the knowledge-driven machine learning, and I've presented those three methods to integrate knowledge, expert knowledge into machine learning, that can be a sensible middle ground to include both the benefits of the machine learning with the expert knowledge that we already have about the process. If we look into the future, what are the big challenges in science and also the industry. So the industry currently uses barely any machine learning systems in manufacturing, which is because certification is so hard. So machine learning network, as I said, it's more a black box. It's very hard to explain. So what we could contribute as scientific or as a scientist from the academic world is more insights into these algorithms. We can, especially explainable AI is a big research field. And if we can provide these insights to the industry, they can then certify the systems to their specifications. And of course, we need to explore more applications for expert systems, but also for machine learning-based monitoring systems. And we need to benchmark them, because in computer science, benchmarking is a completely normal process for all those Google and Amazon machine vision systems. We have huge benchmark data sets and benchmark studies in production environments that is not yet available. So that's also where the academic world can support to create these benchmarks and then aid the industry to decide which system is most suitable. To conclude, to wrap up, I would say that machine learning is a tool. We should not make the mistake to think machine learning can solve all the problems, but it's just a tool among others that we can use to evaluate data. But the actual solution to the problems is a deep understanding of the processes and the data that we have captured. And with that, I would like to end this presentation. I think I'm a bit over time, but if you have questions, I'm more than happy to discuss and answer them. Thank you.